Okay, good morning, everyone. It's the right time to start our class, our lecture. So first of all, I've received some email asking if you want to watch the lecture video online, how do you do that? I suppose everyone knows that, but in case that you don't know that, you can search on YouTube. There's a channel, it's called UFU Data Science. And you just search on that and click into that channel, you will see several courses on that time on streaming, meaning that you can click into that course at the same time you can watch the lecture video. And of course, as we emphasize a lot of times, when the lecture is finished, we will post the link of this lecture video on our course website. To help you, like for example, you want to review the video, you want to look at some discussion of the lecture, like for several times. Okay, so just to give you a hint in case I don't know that. Okay, so in the last lecture, we gave a quick review about some like basic knowledge that will be used heavily in our course. And also I want to remind everyone the deadline of homework 0 is tomorrow, this Friday, May 9th. So according to our office hour feedback from office hour, I know that many of you have already started, but in case that you haven't started, I will highly suggest you to start at least today, right? And need some time to work out those problems and do some practice, and also finish the writing in LaTeX, right? If you never have used the LaTeX before, it may take a while for you to get used to that environment and have everything compiled into a PDF file. Okay. Any questions so far? Okay. Yeah. Let us continue with the supervised learning, right? So in the last lecture, we introduced the general framework of supervised learning, where we have many instances to discuss throughout this semester. But in the broader sense, to conduct supervised learning, you need to define first what is the instance space. Second, what is the label space? Actually, these two spaces define the task you want to do, right? For example, if your task is to classify a news several classes, then your instance space is a set of all possible news articles. Right? And label space is a set of labels you can give or you can tag for every. If you want to predict stock price, and then the instance space will consist of all possible stocks in this world, and the label space will be a continuous space, maybe just no negative real numbers, right? And then we want to learn a mapping from the instance space to the label space, such that this mapping can give the corresponding label for every example in the instance space. We believe that there is an underlying function or ground truth of this target function, right? And we have some ground truth label given by this target function. And the learning algorithm can only see examples of the function f in action, meaning that we're going to collect a bunch of instances and get labels given by this ground truth function. Then we want to run some learning algorithm to search over this target function or ground truth, right? So how do we conduct supervised learning? We're going to prepare a set of labeled training data. You can, in general, view the data as a set of pairs, where each pair consists of the instance and the label given by the target function. So why it is called supervised learning? Because the labels are given, the ground truth labels are given. So it's like you know the answer, right? You know the answer of those exemplar problems. You want to teach learning algorithm what is the right function, what is right labeler, right? So we feed this labeled training data to our learning algorithm. Currently, we can view it as some kind of black box. the learning algorithm will initiate some kind of searching procedure guided by this training data until it stopped and returned some learned function G. Right? And I also mentioned that if you wipe off all the labels here, you only have the instances, you don't have any labels, then the learning becomes the so-called unsupervised learning. If you mix unlabeled examples with labeled examples, it's called semi-supervised learning. So they correspond to different branches of machine learning. However, both unsupervised learning and semi-supervised learning heavily utilize the techniques and ideas in supervised learning. That's why our focus will be the supervised learning. Even we don't have time to talk about unsupervised learning in the future. If you want to study further study on that topic, it's very easy, right? Based upon what we have discussed about supervised learning. Okay. So now, suppose we have finished our supervised learning procedure, right? So we have some training data, and running our learning algorithm gives us the learned function G, right? I will know there's some target function F, right? So a natural problem is that how do we evaluate the quality of our learned function, right? How do we evaluate? Right? You need to know whether this learning procedure is good or bad, right? So that you can improve or you can choose adopt another learning algorithm, right? So now I want to ask, how do you would like to evaluate your supervised learning result? Any thoughts? Yes, yes, exactly, right? So let me repeat your answer. He said that we can use like half of the instances in the instance space for training. Then you can test your learned function on the other half set of instances in the instance space. Yeah, that's right. Right, but here I just want to emphasize first, unless it is totally like a toy case, you usually don't know what is the exact form of the target function. So you don't have access to the ground truth analytical form. In some cases, it might not be like just the elementary function or their compositions. They might not be analytically tractable. Right? You don't have any closed form. So that means it will never be able to, or at least practically speaking, you will never be able to compare the form of your learned function and the exact target function. So then how do we evaluate? Right? As he said, right? We're going to draw a set of test examples from the instance space, right? Then we assume that we're able to get the ground truth label, right? For those test examples. Now we just use our learn function to make prediction. Then we just compare the difference, right? The difference of the ground truth label and the predicted labels, right? If they're completely the same, meaning that I got 100% test accuracy, well, I'm much confident that, okay, my learn function is working well, right? But here I want to emphasize that it's usually not, rigorously speaking, it is usually not feasible to use total half of the instances in the instance space for the training, because imagine that if your instance is represented by like real value feature vectors, so you actually have infinite many instances. So you can only use like a finite number of the training examples for training, and similarly, you can also only use a finite number of test examples for training. But usually, we can assume that, okay, those training examples and test examples kind of representative for this whole instance space, so that our evaluation accuracy on the test examples can indeed indicate the generalization performance of our learn algorithm, of our learn function. Okay. So now I want to ask a question. Can you use test examples during training? No, right? Why? Can you explain why? What? Mm-hmm. Well, I think it might not be precise to say, okay, it's get overfitting, but I know your point. I know your point. Okay, any other idea? Mm-hmm. Okay. Okay. Yeah. 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 Thanks. I think yeah. That's a great answer. So I think unifying the two ideas, I want to explain. I mean, in a more in the most straightforward sense, it means that, for example, I'm not learning anything. I'm just memorizing things, right? And then just memorize things. If I use my test examples during training, I just memorize those test examples. And now during the test stage, you tell me, okay, what's this? Okay, I'm saying this. I just recite the label, right? So it actually doesn't learn anything. You just memorize things, right? So in other words, you can be like, this is kind of cheating, right? And we want to, if you still remember the example pictures, we have shown that if you want to learn to predict whether this picture contains cat or not, right? So you want to gain some kind of generalization ability, right? So for some new image, that cat or that dog you have never seen in your training set, you'll still be able to recognize it is dog, not a cat, right? So, however, if you memorize that test dog in your training procedure, you're cheating. You'll never be able to differentiate, okay, you're really learning something out of some data or you're memorizing things. So that's why we'll never be we'll never allow in machine learning practice to include test examples during training. So that's actually can be viewed kind of overfitting. If you the extreme of overfitting meaning that, okay, you just memorize that example. Right? So but we'll get to the formal definition of overfitting later. So this is a very simple rule everyone should follow during the machine learning practice, but be careful. Many machine learning practitioners, including those highly experienced guys, make such kind of mistakes. So whenever in your study or in your job, if you found your neural network or SVM classifier gets like 99% accuracy, before you celebrate, please carefully check if you kind of mix the training test examples. Right? If you confounded them during the training, right? So I've seen some withdrawn papers from NeuralNIPS, like during my PhD study. That paper claims that, okay, by using their specially designed architecture, traditionally, if you want to do some benchmark tasks, you need to train with some kind of strong GPU. You need to train like at least 1 week. And the authors of the paper claim that using their method, they only need to train for 1 hour. So it's kind of like definitely surprising result. And a lot of researchers from Facebook and Google is requesting for their implementation for the code. And then the authors kind of like postpone, saying, okay, we're still cleaning our code, we're still wrapping up things, and finally it turns out, and then those engineers and researchers trying to replicate their results in the field, and finally the researchers, the authors of that paper withdrew their paper and saying that, okay, they kind of mixed the test examples into the training set, so they can get such good results in 1 hour. So it's a very common mistake during the machine learning practice. So please be careful. Okay, so now I have introduced the framework of the supervised learning. We want to emphasize again the general setting. We suppose that we can collect a set of training examples in the form of the instance and label pairs. And the target function f, of course, is unknown. It's some function we want to estimate, we want to search over with our learning algorithm. And the instance or the input x is typically represented in a feature space. So what's the meaning of the feature space? You can view it as kind of like a vector space, continuous vector space or binary vector space. Like, for example, if your instance is represented by n binary features, well, you can view like, okay, this input vector x, which represent a particular instance, is like n-dimensional binary vector, right? Or some real vector. It's very common that you extract some real value features to represent, say, one image or one piece of sound, right? Collected by your hardware, right? So there is some kind of deterministic mapping from the raw instances to some feature vectors. So before you conduct some specific supervised learning algorithm, you always need to get some feature representation of the instance. Like usually you won't like give a like high resolution image, might be 4096 by 4096. Those many pixels and RGB channels into some machine learning model, it won't be it won't be feasible in most cases because the data amount is too much, right? You need to do some appropriate pre-processing, for example, to convert those raw image into like 100, 1000, even 10,000 dimensional representation of the feature vector. Okay? And although we're not gonna discuss in detail how variety of feature pre-processing or feature extraction procedure is working, but I want to emphasize that in practice, this step is also very, very important. And actually many like recommendation or online advertising tasks, a bunch of a group of engineers are trying hard to work out some new features out of them, the raw click-through data. And then the goal of supervised learning is to find a good approximation for the target function f. And as we mentioned, that it's rarely the case that you can expect you find exact function. It's usually what do we expect? The more reasonable expect is that, okay, we want to find a good approximation such that in many test instances, our prediction is largely consistent with the prediction made by the ground truth. Right? So the last point I want to emphasize, the label space actually determines the kind of problem we have. Like, for example, if you're doing binary classification, that means your label space only contains two elements, right? Positive label and negative label. If your label space is kind of discrete, finite, discrete, 1, 2, 3, 4, 5 to k, then that means you're doing some multi-class classification. And if your label space is continuous space, it's a real space, that means you have like infinite uncountable elements, then this task usually is called regression. Okay. So any questions so far about the general setting of supervised learning? Everyone is comfortable? Anything weird? Okay, great. So whenever we want to conduct some supervised learning task, we need to answer the following questions. Right? That's also when you start doing your project, right? No matter it's Kaggle computation or perhaps the Kaggle computation, we have already defined the instance space and label space for you, right? But how do you choose the specific learning algorithm? How do you combine them together to submit your solutions? You need to answer the remaining questions. And for exploratory problem, you need to formulate the problem itself. That means you need to first answer what is your instance space, what is your label space, right? What is your task? And then once you have formulated your prediction problem, your learning problem, right? Then you need to decide what is your hypothesis space. What is hypothesis space? Right? The meaning is that okay, the candidate or set of candidate functions over which you want to search. Right? Remember, the learning algorithm essentially is a searching procedure. You want to search over some space, some family of candidate functions to find one which is closest to target or closest to the ground truth. Right? Of course, before the search, you need to determine the search range. Right? You cannot say, okay, I'm gonna search over the universe. Right? That's not feasible. Right? You always need some kind of assumption about the function family, which you believe you can find one closest enough to the target function. Right? And once you identify the search range of the function, then you need to decide what is a particular learning algorithm. Right? As we mentioned, learning algorithm essentially is a searching algorithm. Right? So you need to decide what kind of principles, what kind of rules is going to conduct the search. Right? In a lot of cases, you will see that we use some gradient-based approach. Right? So using gradient-based optimization essentially is also searching procedure. Right? You're searching over continuous space. You use gradient to guide you to move toward some kind of local minimum or local maximum of your objective function. Right? And then, of course, in several algorithms we're going to discuss, including decision trees, they're not like gradient-based approach. You see that we define some heuristic searching procedure to identify the target function, but unfortunately, it is not the exact function. It's kind of approximation to the optimal function we want to look at. And finally, once you have identified some specific function as our learn result, right? So you need to define some kind of evaluation metric, right? And every time you finish that, of course, you need to know some feedback. You need to know whether your result is good or not, right? And based upon that, you can make some kind of improvements. You can switch to other more promising methods, right? So you need to define some value evaluation metric. And actually, you will see that your training objective or training loss function is often defined on this evaluation metric as well. So basically, it's oftentimes that you're going to first define the evaluation metric, and based on the evaluation metric, you're going to define some loss function over the training data. Then you optimize that loss function to guide your searching procedure. So the evaluation metric is not only useful for the test stage, but also very important in the training stage. We'll get to that by looking at several instances of the learning algorithms, so everyone will get clear about this point. Okay, any questions so far? Great. So here's just a brief taxonomy. We got supervised learning is a big branch, and it's unsupervised learning, semi-supervised learning. And here are a set of different supervised learning models or algorithms I want to discuss in this semester, like decision trees, like boosting, ensemble learning, random forest, linear models, including linear regression, logistic regression, naive Bayes, perceptron, support vector machines, and so on, and nonlinear models like nearest neighbor, polynomial regression, kernel methods like kernel SVM, kernel perception, or artificial neural nets, and so on. So you can see that there are a lot of instances of supervised learning. And we're gonna start with decision trees. Okay, so here is our plan for the decision tree topic. So we're gonna first talk about what are decision trees, right? What's the definition of that? We'll introduce decision tree in terms of representation. You see that decision tree essentially is kind of like compact summary or compact representation of the data, right? And then we'll introduce some well-known classical algorithm to learn a decision tree out of data, or in other words, to create decision tree to summarize data. You can understand them either ways, but they're the same. And we'll introduce this so-called ID3 algorithm. This is a recursive algorithm, meaning that it is gonna like recursively call itself to create new subtrees, new branches and nodes until they have arrive at the leaf nodes. Right? This will be the key component about our decision tree algorithm, and this is also the algorithm table you are requested to implement in your homework 1. And then we're gonna discuss several variants or extension of the decision tree learning algorithm. So you see that ID3 algorithm is not 100% enough in practice, because in practice you have to deal with like the dirty data, right? A lot of other stuffs. So sometimes the tree is growing too much. This is not what you want, because it can incur overfitting. We're going to discuss what is overfitting, why it's harmful, why we don't like overfitting, right? In that case, you need to control the scale of your trees. That means you have to prune the trees, perhaps, right? So we're going to introduce several methods, like you can control the tree growth during the training procedure, or you can first grow the full tree and do some post-pruning procedure. Okay? And also, we'll introduce some other node splitting principles when you create the trees. And all those principles are used to measure the same kind of thing. Right? We'll discuss about that later. Okay, so before we talk about decision trees, why I would like to highlight decision trees, right? What's the motivation of using decision trees? Right? So the first motivation here is that they are simple and intuitive. Okay? So you see that it has a nice structure to collect a set of rules. Right? It's very like how human beings are thinking about problems, right? When you look at something, when you learn something from experience, like by default, I guess everyone's brain will kind of come out with some set of rules, right? Rules of thumb. And next time I meet some kind of similar cases, I just look at my rules of thumb. I follow my rules, right, to avoid mistakes. Right? So decision trees follow the same procedure. Right? They look at this supervised training data, right? Then they want to extract a set of rules to tell under which kind of cases or circumstances, what kind of labels should we predict, right? And you just use these rules to make a prediction. And also, it brings a lot of interpretability, right? So when you look at the learned decision trees, you can very easily to extract every line of rule, right? You can look at why the rule is composed in that way, right? This is very important, like in medical applications. If you look at machine learning papers or so-called machine learning papers in medical journals, a lot of them are using decision trees or random forest rather than like black box neural networks. Like if you use like 100-layer deep neural nets or ResNet, well, sometimes it gives you surprisingly good results, but you don't know why. Like you can't tell why it gives a diagnosis of cancer, right? You need to explain to the patient, right? You're okay, you're fine. You have some illusion about your symptoms, you're fine, or you're bad. You should prepare for some treatment, right? You need to give some explanation, right? And decision tree is excellent in the interpretability. Although in terms of predictive power, it might not be as strong as neural networks. Okay. But the third point I want to emphasize that although a single decision tree might not be like powerful enough as compared with very strong classifiers like deep neural nets, but it can be promoted to be very, very strong by using some kind of ensemble learning technique like boosting, random forest, and gradient boosting trees. So this will be the following topic after decision tree. And you see that the classical algorithm on emphasize is called AdaBoost. It's just is a first very widely successful boosting algorithm based on decision trees, and it's actually the default algorithm in most digital cameras. The application I mentioned before, every time you use your digital camera, it can automatically bound in faces. Right? It is typically implemented by AdaBoost. And the gradient boosting trees, we don't have time to go to that. But I'll tell you that gradient boost trees is kind of a state of art in recommendation and online advertising. So I once met some research engineering in Alibaba. You can basically view as a Chinese version of Amazon. And he told me that actually industry, at least in Alibaba, he never the deep learning or deep neural nets has never have like strong evidence to beat gradient boosting trees. But good thing about gradient boosting trees that it's very, very fast and efficient to train. You don't need to train. You don't need to buy like a million GPUs and run them on GPU servers. And gradient boosting tree, you can just run some workstation. It can give you very decent performance in minutes. Yeah, finally, I want to emphasize that decision trees, although they were invented, I think 40 years ago or 50 years ago. I can't memorize, but it's old, but it's very, very widely used and has many, many successful applications. Okay, so first, I want to talk about what are decision trees. Right? So before we get to some detailed example of decision trees, I want to give some summary of that, give you some kind of a sense, and then you can map what you have saying to this several points in the definition. Right? So overall, decision trees are kind of like a hierarchical structure that represents data with a divide and conquer strategy. So divide and conquer is kind of like classical technique, right? You want to address the complicated problems, you want to divide and conquer, right? And this is a kind of divide and conquer representation of data. And you see that in decision tree, each node represents a subset of that data. Of course, the root node will correspond to the whole data set. And then every node in the middle represents one subset. And each node is also associated with a test feature. What's the use for this test feature? This test feature is used to create new branches along that node. Right? So from the node, one branch is created for every value that feature can take. And then by filtering out examples that taking that feature value, we can further partition data. Like, okay, for this particular node, which represents maybe just 50 examples, right? One subset of the whole data set, right? And now it is associated with one particular feature like gender, right? And you got maybe or maybe age, right? You got like 3 levels, like you got young age, you got old age, you got middle age, right? You're gonna accord to the level of age each example take. You're gonna partition them into these 3 subsets, right? And each subset is connected to the original node through one branch, right? That branch has one feature value attached on. That's the basic idea. But if you still feel unclear, that doesn't matter. We'll look at the example immediately. Right? So what do the leaves of the tree mean, right? So leaves of the tree specify the class labels. And also is the point where we stop the partition. So in the ideal case, a leaf of the decision tree means that the associate subset are uniquely labeled. Right? Like 10 examples are on this leaf node, and all these 10 examples are labeled by, say, positive, then it must be a leaf node, and then we have some label on that leaf node. Okay, so the general idea of decision tree learning essentially is to give a given a collection of labeled examples, we construct a decision tree that hierarchically represent that. So now with those points in our mind, let us look at some detailed example. Right? Let us build a decision tree for this data set. Right? So this is a set of color shapes, right? We got red, green, and blue, right? We got circles, rectangles, and triangles, right? And for every color shape, it has a label, either A or B or C, right? We want to build decision tree to hierarchically represent this set of color shapes, right? So that to give you a concrete idea, the definition of the decision tree, right? But before we build the decision tree, right, I want to ask you to observe those data set and give me a guess, right? So if I now give you a red triangle, which label would you like to predict? Why? Why B? Yeah. That's a very, very good intuition, right? Because no matter what shapes those red ones are, right? They all belong to class B or category B. So of course we have a reason to believe that even I switch to a new shape like triangle, as long as color is red, it should be B, right? So that's right. And you will see that when we create decision tree to represent this data set, then use that decision tree to classify red triangle, it will give you the label B. Okay, so to create a tree, we need to first look at what are attributes of each example having, right? We got two attributes, right? Each example, each color shape has two attributes. One is color, one is the type of the shape, right? As we mentioned, we might have a blue, green, and red, right? And the shape type can be circle, can be rectangle, can be triangle, right? So now we want to use these attributes to gradually partition those data set, right? So suppose we use color, right? We first use color. So we have three possible colors. Right? Oh, by the way, I would like to emphasize again, when we start to build our decision tree, we start with some root node, right? This root node is associated with the whole data set, right? Every time, and also associated with some testing feature. Here will be color, right? We just pick up color. So then we look at how many particular values the color attribute can take. It can take three possible values: blue, red, and green. And because this root node is also with whole data set, now according to each example, the particular color value it can take, we can partition the whole data set into three small subsets, right? That means the blue shapes, the red shapes, and the green shapes. Does it make sense? Yeah, we just partition the whole data set according to their color. That's what we do, right? So we can first look at the middle one, the middle subset, meaning that all the shapes with red color, right? So what can we see? We can see that all the red shapes have a unique label, which is B, right? So that means we're going to stop here. As we just mentioned, if the subset of the examples are uniquely labeled by one label, right? Or they share exactly the same label, is useless or is meaningless to do the further partition, right? We'll just stop there. Then we'll create a leaf node and give the label B on top of that. Right? Now let us look at the other two subsets, right? The left subset are blue shapes, right? So how those blue shapes are labeled? Are they uniquely labeled? No, right? We actually have quite diverse labels among blue shapes, right? We got blue rectangle, blue triangle, and blue circles. That means our partition cannot stop, right? We need to further partition those blue shapes, right? And now the color attribute has already been used. Then we're going to use the remaining attribute, which is the ship type, to further partition the blue chips. Okay. So now we further partition this subset according to the ship attribute. Now the ship can take 3 values. Okay. Triangle, square, and circle. Now if we look at blue triangle, we see that we have 2 blue triangles. They are uniquely labeled by B, right? So mean that we have arrived at a leaf node, okay? Because of the subset. All the examples in this subset share the same label. Okay? We're gonna stop here, then we create a leaf node, we give the label B. And how about this one? The blue square, right? How many labels do we have for the blue squares? Just one, right? There's only one example, one label. Okay, the subset is unique labeled. So we create a leaf node, we stop here and give a label A, right? And similarly, when we look at the blue circles, we got 2 blue circles, they're uniquely labeled. So we create a leaf node and with the label C. And similarly, when we look at the right branch, right? The green shapes. Right? The green shapes, how many labels do they have? 2, right? We got label green. We got these 2 green shapes labeled B and these 2 green shapes labeled as A, right? So they are not unique labeled. So we haven't. We can now stop. We need to further partition them according to the remaining attribute shape, right? So we're going to use this shape attribute to further split the associate subset, which are green shapes, right? And the shape attribute can take square and circle on the 4 objects or shapes in this subset, right? So we're going to grow 2 branches. One is the shape takes the value square, right? We got all green rectangles, which are labeled as B. So create a leaf node with label B, right? And for the green circles, right? They are both labeled as A. So create a leaf node with label A. Okay. So now we have arrived at all the leaf nodes, right? So our tree construction is completed. Any questions so far? Mm-hmm. How about there's a blue square in label C, but it will still be, that means you have 3 blue square in label C. Oh, okay, that's a good question. That means we have exhausted our feature set, but your data set is still not uniquely labeled, right? So in that case, you still need to stop because you don't have additional features to further split the data set. Then you need to pick up the label to represent that leaf node. And here we're going to use the majority label, right? Yes. That's a very good question because this will be the corner case when we discuss about our ID3 algorithm. But yeah, it's very good that you point out this concrete example for that. Yeah. Mm-hmm. If you're talking about ties, right? Like 2 are, say you have 2 blue square labeled as C, 2 blue square labeled as A, and then you can pick out whatever. Yeah, that's a kind of just a rule of thumb. Of course, if you have some prior preferences, I believe that even they have the same amount of labels, but I do believe label C is better. Then you can use C. Okay, but without any preferences, you can pick up whichever. Yeah, that's another good point. Ideally, we want this tree to be as small as possible. Why should we make such kind of assumption? Because it fits the so-called Occam's razor principle. We'll get into the definition of Occam's razor principle and why it's rational later. But you can simply will it, okay, suppose I got 10 trees. Each of tree can well represent the whole data set. Which tree would you like to choose? You would like to choose the simplest tree because it has the least complexity. So basically, the Occam's razor says that, okay, without necessity, don't increase the model complexity. Right? That's kind of like a philosophical choice rather than some like mathematical improvement. But we'll see that in the following lectures when we introduce computational learning theory, variance and bias trade-off, you see this kind of Occam's razor principle is repeatedly reflected by those mathematical statement. Oh, you got a question, right? Yeah, that's another good question. Actually, because the data set are varying, right? The features are varying, and different the range of the feature values are varying as well. You cannot hard code that, right? We must develop some kind of like generic algorithm, right? Can deal with all kinds of features and their values. We must have a smart choice of the sequence of features to split the data, right? And regarding how we do that, we'll talk about in the ID3 algorithm, and we'll talk about why we make such kind of choice. Right? ID3, as we mentioned, is a greedy heuristic. It's not like a global optimal algorithm which guarantee you to find the smallest tree. But we'll talk about why we can only apply a greedy heuristic in practice, because searching a global optimal tree is NP hard. We cannot make it work in efficient in practice. Mm-hmm. Mm-hmm. Yeah, there will be another tree. Yeah. Right now we're not learn that, because the learning will refer to, okay, how do you determine you're gonna first use color to split, or you're gonna first use shape to split, right? It's not enumerating all possible trees. So want to find an efficient way to determine all the features you use to split the data set gradually and return to you a kind of relatively small tree. That's our learning goal. But what you mentioned is that you're right. Like if you start with shift to split data, the tree structure is different. Right? And then there's another question, right? Which structure is better? Right? So actually, at end of this part of slice, there's one problem asking you to manually construct a tree by using shape first and then color. And I want you guys to it should also include in homework 1. I want you guys to also do that to have a sense what's the difference after you using different order of the features to split data. Okay. Mm-hmm. What? First, how is it different from what? Flowchart. I don't get your point. What do you mean by flowchart? Oh, that's about the algorithm table, right? So, yeah, let us talk about that in more detail in the ID3 algorithm framework. Well, right now the procedure I give you is that, okay, I pre-assume I have determined the order of the feature list I want to use to create the tree. So that is pretty straightforward, right? Just pick up the first attribute, split them, and then pick up the remaining and go on. It's intuitive, but when we integrate the choice of the order of the features every time, this is totally different. Any other question? Introduce what? A green triangle. Yeah, that's a very good question. So let us hold up this question because this is a question I want to ask you guys in a minute. Okay. Okay, so first, let us look at the tree we have already manually constructed, right? You can this is a classifier. You can use that to make prediction right now, right? So now I want to give you some kind of prediction rule based on this tree, right? So if I want to predict the label for the red triangle, given this tree structure, how do you do that? Any thought? Yeah, it's very intuitive, right? You start from the root node, you look at test feature, right? And you just look at which branch matches your example, right? Then you move to the next node, right? And then you look at the associated test feature, you look at the corresponding value of that test example, follow which branch. You just continue doing this until you arrive at a leaf node, right? And then you just use that label to make prediction. Like if you use red triangle, you want to test label for red triangle, you look at the color, right? This is the test feature associated with the root node. Okay, you see that, okay, for the color, this test example is feature value is red, right? Then you just follow the middle branch, right? And then you have arrived at the leaf node. Right? It tells you the label is B. Then you just predict B. That's it. So it's very, very intuitive, right? So now that comes the question he mentioned, right? So suppose our test example now is a green triangle, right? What's the problem of making prediction with this tree? I wouldn't say it's a training label, but let us just apply. Yeah, let us just apply this tree to make prediction, right? And see what happened, right? So of course we start from again we start from the root node where the test feature is color. Well, the color attribute for this example is green, so we follow this branch, right? We arrive at an intermediate node. So now we're gonna test the shape feature, right? So the shape feature that this test example taken is triangle, right? But now we comes the problem, right? We comes into the problem that we don't have any branch following the triangle, right? The triangle value. And unfortunately, this is just an intermediate node, it's not a leaf node. Okay? So it doesn't provide any label. So that means you're just stuck here. You're stuck here and you cannot make any, you can not make any prediction on that. So I would like to ask you to think about a question a little bit more in depth, right? What's the problem? Why we have had such a problem? Well, maybe starting with shape can address that problem. Yeah, you're right. But here, let us assume now, okay, we indeed first use color and then use shape to construct such tree. And why? How can we remedy this problem? Mm-hmm. Yeah, I think you're getting to the point. Let me, any other comment on that? Okay. Mm-hmm. Mm-hmm. Yeah. It's more like I think it's more straightforward explanation on that. Okay, let me unify both those points from you guys, right? So the reason we come out of this kind of problem is that, okay, when we split this green shapes, right, this subset of green shapes, we actually lack some attributes value like triangle. So you don't have any green triangles in your training set. That's why you actually don't have a third branch here. Right? Then when you really test a new example which has triangle shape, and then it's stuck here. So of course, we can address that problem if we can collect more abundant data, right? That's one way. But a more robust way would, okay, even my subset of data doesn't contain some particular feature value, I'm gonna still create a branch, right? To match the case every value that attribute can take. Then the remaining problem is that how, if we create a triangle branch here, we know that the associated data subset is empty, right? Because we don't have a green triangles in our data set. Then the problem is that for this fabricated empty subset, what kind of label should we assign? Okay. Right? All of B. Yeah, that's one choice. Any other suggestion? Yeah, that's actually the most common choice, right? So now that if I just create the new subset called green triangles here, it's empty, right? We don't have that in the training set. So I'm gonna step backward. One step, look at this green triangles. This subset, I just look at the most common label, I assign it. And if there, and someone asks, okay, do I have even like more general choice? Like, can I move backward to the root node and pick up the most common label? The answer is yes. I just gave you the most common choice. You can just go back one step forward and look at all the green shapes and use the most common label among the green shapes as my label for this virtual node. Yeah, we'll talk about those are all important corner cases we're going to discuss when we for the ID3 algorithm. Otherwise, if you do not pay attention to those details, it will be the case that you run an ID3 algorithm. Sometimes it's just stuck there, or just crash. Okay, any question? Okay, great. So, given this tree, right? So I want to look at what decision functions do decision trees represent. Basically, what kind of decision functions we use to classify every possible instance, right? So as we mentioned, when we make a prediction, we start from the root node to look at the test feature, and then we follow a branch where the test example matches the feature value. Then you arrive at the second node and look at test and feature, and then do that again and again until you reach to some leaf node, right? So this actually represents one path from the root node to a leaf node, right? So in the whole decision tree, every path from the root to the leaf is a rule, right? It's actually a decision rule to make the classification result, right? And the full tree is equivalent to the conjunction of all rules, right? We can write down our decision tree in a more formal or mechanical form, right? So this is our tree, right? You can enumerate all the paths, right, and do the conjunction, right? So this path means the rule that if color is blue and the shape is triangle, then I can conclude that label is B, right? I can predict label is B. And if color is blue and the shape is square, then I conclude label is A, and so on. Right? So now we can see why we claim that decision tree is interpretable, right? Because from the tree structure, we can just enumerate all the passes, and each pass correspond to one rule, right? We can look into those rules and to see if this rule makes sense or why this rule makes sense, right? It's not like a neural network, you got some linear transformation, nonlinear activation over every elements, then do a linear transformation, nonlinear activation at every elements, and again. And once you come out this decision function, you don't know what it means, right? It just tell you, okay, in this case, it is positive. In that case, it is negative. It's very hard for the for extracting the meaningful knowledge from your learned classifiers. Right? But decision tree is much more transparent. So far, the decision trees we have seen are making discrete classification, right? So we want to, the outputs are discrete categories, like A and B and C, right? Like positive and negative, right? But I would like to see that the if you want to make a regression, meaning that our prediction is a real value, this is also possible. But how can we do that? Any thought? Assign how we send. Mm-hmm. Oh, that's well, the idea you mentioned is more like how do we deal with numerical feature values, right? But here, let us first consider about if we want to predict some continuous label, like the temperature, like snow precipitation, right? Or stock price. How can we do that? Actually, in most of the cases, we just use a naive approach. We take average. Of course, you need to specify a criterion that you create a leaf node. You're not gonna further split the set of examples, right? And then you know that, okay, this small subset of examples on the leaf, they have different continuous outputs, right? And then to generate the final output for that particular leaf, a most common strategy will be just take average, right? And example 1 got output 0.3, example 2 got output 0.1, example 3 got output 0.25, you just take an average. Right? The other could be like you take a median. But you just come out with some way to aggregate the outputs of the examples on that leaf node. You use that as the output for the leaf node. Then we can do the regression. So this is called regression trees if you're using decision tree to regress continuous values or continuous labels. And later we'll discuss about methods for handling noisy data. Like if you have noises in the label or in the features, if you just run decision trees without decision tree algorithm without any modification, you might have some trouble, which is called overfitting. You may create too large trees, and you need to control the size of tree, right? Okay, the second problem is that the instance we have seen so far, the attribute values are always discrete or categorical, right? Either blue, yellow, blue, green, or red color, or the shapes is a triangle, rectangle, or circle, right? So what if we have numerical feature values like height, like length, right? Like wind speed. Right? In that case, how can we use them to create new tree branches? Mm-hmm. Yes, exactly, right? So in this kind of case, we're going to first bin them into several bins or discretize them into several ranges, right? You just check if your numerical feature value falls into some specific range, then you map it to categorical 1, 2, 3. You essentially discretize the numerical features. That's it. So now I want to show an example that you got two numerical features, x and y. Okay. Of course, you use original x, y values, you cannot create decision tree. But now we can first discretize them into several regions. Like for x, we discretize them into three regions: less than 1, between 1 and 3, and bigger than 3. And for numerical feature value y, we got three beings, right? Less than 5, between 5 and 7, and bigger than 7, right? Those are the labels, right? Those are the labels of the training examples. And then according to those discretized features, you can create a decision tree like this. Right? If you start with x less than 3 as the root node and testing feature. So by the way, when you do the discretization, you can will either your x value falls in some region or not as a one binary feature. So you got three regions. That means you actually have three binary features. Right? And similarly, you discretize y into three regions. Then the y value falls in one particular region corresponds to a one binary feature, yes or no, right? And falls in this region between 5 and 7 is another binary feature. Less than 5 or not is another binary feature. You actually expand the feature list, right? But each feature is relatively simpler, right? So I won't show how we manually construct this decision tree, but I would suggest you guys to replicate the tree construction, right? So here I want to emphasize that although the decision tree looks kind of pretty straightforward, a naive classifier, it doesn't mean it is a very simple classifier. How can we see that? Right? So we can see the decision boundaries, right? Namely, the boundary which separates the positive and negative examples. You can see that this is essentially nonlinear, quite nonlinear boundary. Okay? However, when we later talk about linear classifiers or linear classifiers, you see that the decision boundary for linear classifiers is always a line or just a plane. But for decision trees, you can see just two features that give you quite complicated decision boundary. So decision trees are not as simple as it looks like. Okay, now we come to the summary of the decision tree representation. We can view as a compact hierarchical data representation, right, from the root node, which represent the whole data set, and then do this level by level. And each intermediate node represents one subset of the data set, and also associated with test feature, based on which we further grow the branches and new nodes, right? And predicting with the decision tree is very easy. And it just find a path from root node to some leaf node to match all the feature values that test example takes, right? And clearly, as we discussed, right, given one data set, there can be many decision trees that can represent, right? Why you can just switch the order of the features or attributes you use to create the tree. You see different structure, right? Here's one exercise, which I encourage you to do after the class is that, okay, with the same data set, now you manually construct a tree, but first use shape and then use color. Then compare the tree constructed in our class, right, in our lecture, and see the difference. Okay, any question regarding the decision tree representation? Hopefully this is intuitive and everyone feels comfortable. Okay. So in the remaining 10 minutes, we're gonna start. We're gonna give a start about the decision tree learning. Oh, sorry. Going to hide the floating panel. It's now okay. So we have a introduced the representation, right? Now we'll come to the algorithm. Right? We need to develop some automatic algorithm which can construct the tree from data, right? And the algorithm not only helps you to create the tree, right? But also you need to determine at each step, which attribute we're gonna select to create our tree. Right? So we're gonna focus this so-called ID3 algorithm, which is the classical decision tree learning algorithm, and it's kind of a backbone of the modern implementations, right? So you see that essentially it is a greedy heuristic algorithm, and we will explain why it's greedy heuristic. Right? But before that, we are gonna give a brief history about decision tree research. So it can be retrospect to as early as 60s in last century in the psychology department. That's why we emphasize that decision tree is intuitive, because the tree structure were originally used for those psychologists to study how human beings are thinking and reasoning. Right? They found that the human learning and reasoning procedure follows some kind of searching and tree structure. And then there's a milestone that in late 1970s, Quinlan, he's a pioneer of artificial intelligence. He developed the so-called ID3 algorithm and uses so-called information gain heuristic to learn the expert system from examples. Why it's called expert system rather than AI system rather than machine learning? Because in that time, like late 1970s to 1980s, there's a very hot topic in artificial intelligence called expert system. And if I'm taking artificial intelligence course, you should know that you should have learned that the expert system was invented by 2 Stanford professors and showing that effective in many applications. So then at that time, expert system just means in most cases just means artificial intelligence. Right? And then then later there are 3 statisticians developed the so-called CART. Right? It's a suite of decision tree learning algorithms, not only for classification but also for regression. And this CART mainly uses another type of measurement. It's called the Gini index. We're going to discuss in our class as well. It's not information gain. It turns out that the Gini index is more robust. And then in the 1980s, there is a variety of implementations for decision trees, especially to handle data noises, continuous attributes, means how do we impute busy data, all kinds of stuff, which we're going to cover in our class. And then in the 1990s, Quinlan has released his updated version of ID3. It's called C4.5, and then C5.0. And unfortunately, C5.0 is only commercially used. That means you need to buy them to use them. I got a chance to run C5.0 during my master program, and it was built in some professional data mining software. It really works well. It works really well. I mean, it's kind of as good as a neural network, and also very fast. Although I don't know what are the algorithmic details in C5.0. And then later, with the arising of the ensemble learning techniques like boosting and bagging, and decision trees are becoming kind of like a basic unit in constructing those more powerful ensemble learning algorithm, like random forest, like AdaBoost. Okay, throughout the discussion of ID3 algorithm, we're going to use one concrete example. Like, we do not plan to talk about the algorithm table in a very abstract way. We want to use some concrete example to showcase how each step this algorithm runs. Right. So this particular example we use is to learn decision tree to predict whether I'm gonna play tennis today. Right? So the decision is up to 4 weather features. Right? Outlook, temperature, humidity, and wind. Of course, for simplicity, here we still assume all those features are categorical features. So all of feature can take three values: sun, overcast, and rain. Temperature has three levels, like hot, mild, and cool. And the humidity has three levels as well, like high, normal, and low. And wind has two levels, strong and weak. Right? And because my decision is binary, either I stay home or I come outside to play tennis. So it's a binary classification task. We got binary labels. So suppose we have collected 14 training examples, meaning that the past 2 weeks, the weather conditions, and also my decision to play outside or not. Right? So those column just index those examples, and for simplicity, we just use the first letter of the feature name and the feature value to represent the particular feature name and the feature values for each example. Right? So if we run our ID3 algorithm, we will recursively build decision tree in a top-down fashion for this 14 examples. This is where our decision tree is generated. It will first select the outlaw feature, and then partition these examples according to the values like sunny, overcast, and rain. Right? Then in each subset, they're gonna further select from the remaining feature to do the partition. Like in this branch, we have like humidity to split, and then we get 2 leaf nodes. And in the overcast examples, we directly arrived at the leaf node, and for the raining examples, we only need one more feature, wind, to do the partition. Then we'll arrive at leaf nodes. Right? So you can see that by running ID3, it gives you a pretty shallow and simple tree structure, which will represent the whole data set. Okay, so let's stop here today and give you kind of like sense an example we're going to discuss about decision tree. On next Tuesday, we're going to discuss about detail about ID3. Okay, thanks. Temperature should be what? No, it doesn't select temperature. It's not necessary to use up all the attributes. It just uses a small subset to arrive all the leaf nodes. Yeah, that's one goal of this algorithm. I want to use as small number of features as possible to split data. Yeah. Thank you.
You asked us to answer condition code. So I have been half an hour homework. You asked me to do it. You were to submit this Friday. And half of it, but the payment fee by tomorrow. So I need to decide which class to put. So will I be able to get a permission? What should I do? Next.
You want what permission code?
Yeah.
You just 1 second.
Yeah.